Hello, and welcome to everybody to today's Ethereum Classic Technical Showcase. So I'm Tim Harrison from IOHK, and this is the third in a series of showcases where we're highlighting some of the developers from the ETC community, looking at the 51% attack conundrum and how we might want to solve it together as a community. So the purpose of this series is to introduce some of the ECIPs from several different development teams, including IOHK, who led, but also we've had a couple since then, to look at the engineering approach and to share it with the community and give you an opportunity to ask questions as you look at those technical solutions. So today we've got Sergio and Martin joining us to share their proposal and to take your questions at the end. We'll hand over to them in a minute. Now, if you do have any questions, you'll see in the crowdcast, if you're watching live, that there's an ask a question section. Please add your questions into there and upvote the ones you feel are the priorities. If you're not watching this live, you're probably watching it either on the Crowdcast platform afterwards or on YouTube. Please feel free to make any comments and we'll have a look at those as well at the same time. So we've got up to an hour today to go through the proposal and take any questions, depending on how many questions we get from the community. So really what we're focusing on today is the technical side of things. We're not looking at the implementation, any detailed timelines, and we don't want to go into the philosophy of some of these ideas. But this is really, as I say, a showcase for you to understand what is the technical solution being proposed. So we'll hand over to Martin and Sergio in a moment. But before I do that, perhaps I can just hand over briefly to my colleague, Brian, who's also been looking at this process. Brian, perhaps you just want to say a few more words about how the rest of the process will work.
Yes, thanks, Tim. Yeah, so this is the third in the series, and we're hoping there's going to be one more later in the week also. So as Tim mentioned, the purpose of this meeting is to be a technical presentation from IOV Labs on their proposal for 51% attack resistance. So like as before, this is an education session, and we want the community to get to a point where they have an informed idea of each proposal and the trade-offs and the pros and cons of each one. So we're not comparing right now today, or it's not a debate on the comparison between each of these proposals, but it's just to give these proposers the opportunity to educate you guys and explain in detail their proposal so everyone can understand it and what they are planning to do if it gets accepted. So this should be a collaborative process where we get to know each other, work together to arrive at the optimal solution so that everybody's happy with the solution that's chosen in the end, right? So whether that one is RSK, Veriblock, ParallelGuard, or IOHK, or another one. So yeah, that's it. So once we get all these series done, we'll move on to a comparison stage where we can look at the pros and cons of each one, and importantly, the practical elements of each implementation and the philosophical elements of each implementation as well. So right now I'm going to hand it over to the guys. Sergio?
So, HK for the opportunity to present along with you. Well, my name is Sergio. I work in IOB Labs, in particular in research and innovation in the RSK node. Well, we put up this proposal for the Ethereum community, the Ethereum Classic community, very fast. There was a lot of different design choices. So in this presentation, we will show just one possible implementation of our solution. Thank you very much for being here. Martin?
Thanks, Sergio. So welcome, everyone. I'm Martin. I work along with Sergio at IOV Labs. I'm the responsible for the mining team over there. So we do many things related to mining, hash rate, and mostly Bitcoin merge mining, which is what our platform uses. But now, this time, as Sergio said, we've been going back and forth with different proposals in order to also help the mining community. That's also one of our goals. And that's why we pulled up this proposal, what you're going to see today. So with no further introduction, I think it's time for Sergio to start presenting that. Hope you enjoy it.
Okay, I hope you all are seeing the screen right now. So this is the presentation for ECIP 1096, which is a 51 attack protection system for Ethereum Classic based on Bitcoin merge mining. And we have already presented ourselves, so let's start. So what's the motivation for this proposal? Ethereum Classic has been subject to several 51% attacks. We all know it. And this was due to its low ETH hash rate. Monitoring the hash rate through NiceHash has not been enough to defend from these attacks because it's easy to hire GPUs to perform this attack. So NiceHash is not the only way you can get the amount of hash rate to perform a 51% attack. The Ethereum Classic community wants to keep Nakamoto consensus, but it's willing to accept slight modifications to overcome the current problems, possibly temporary modifications. What are the design constraints? First, this protection system should be temporary, at least should be very easy to take out if the community really wants it. This is because Ethereum Classic community has already chosen to move to SHA-3 mining. So the protection should be easy to implement. It should not imply much higher centralization. We hope that our proposal does not imply any centralization, but this of course, is somehow subjective. And we will assume that the Bitcoin blockchain will not be reverted to a double spend Ethereum Classic. So because the Bitcoin blockchain is not reverted, let's say 100 blocks to double spend Bitcoin, then we can assume that the same will happen and it won't be a target to revert Ethereum Classic. So first, a few words about merge mining so that everyone can understand our proposal. So merge mining is a process where miners secure more than one blockchain at the same time using the same machines and the same electricity consumption. So one blockchain is considered the primary blockchain and the other are considered a secondary blockchain or auxiliary blockchains. And this is not because one blockchain is connected to the other in any way. It's just because one of the blockchain block headers is the one used to store a Merkle tree containing the other blockchain's block headers, or the other blockchain's hashes of the block headers. So that's why one is primary and the other is secondary. But apart from that, I would say format of the merge mining proof, there is no other technical relations between the chains. Each one can have different rates or different subsidies, and there's nothing else that connects them. A few words about RSK. RSK is an EVM-based blockchain similar to Ethereum Classic. We do merge mining with the Bitcoin and also with Bitcoin Cash. About 50% of Bitcoin hash rate is currently secure in RSK. And we have also an Armadillo, the Armadillo system, which is a fork monitoring system that we will talk a little bit more about what does fork monitoring bring and how can we make this secure. And it also has a federated POPEG with Bitcoin, which means that the Bitcoins that come into RSK are locked in a multisig, protected both by hashing power, by hashing rate, and by a federation. Okay, so what is this design space for a 51% attack protection based on Bitcoin merge mining? Well, there are a lot of choices, and in this presentation, we try to narrow the design space to what we think that would be best for the Ethereum Classic community. So we can make the Bitcoin blocks contribute to the Ethereum Classic cumulative difficulty or not. We can create a separate subsidy for Bitcoin blocks or not. We can make these on-chain messages or off-chain messages, and we can perform consensus changes or not. So there are a lot of variables we can play with, but we have chosen in this presentation just one set of possibilities, right? So what is fork-aware merge mining, which is basically what we are proposing to help Ethereum Classic. So blockchains that merge mines with Bitcoin can capture 100% of Bitcoin security against double spends, which is the persistent property. So this is something that not people are aware of, that even if you had, let's say 1% of Bitcoin blocks merge mining your blockchain, then that can guarantee the persistent property of your blockchain. If you are willing to trade off liveness, the liveness property in case of an attack. So if you can detect parallel forks or that an attack is ongoing and switch your full node into a safe mode where it does not finalize transactions, it does not confirm transactions, then you can actually get 100% of the thermodynamic security of the Bitcoin blockchain, even if you have much less than 50% or 51% or 100% of the hash rate. So how we managed to do this? Well, with a combination of techniques. One is obviously the checkpointing of a Ethereum Classic block into Bitcoin. The other is by linking the timestamps, so making sure that the Bitcoin timestamp do not differ much from the Ethereum Classic timestamp. And we also need the decentralized monitoring system to detect these forks, to detect this Bitcoin hash rate that is attacking. And finally, we need some kind of penalization system when blocks are delayed, when blocks come without, these Bitcoin blocks. So this is how I see the merge mining security hierarchy. So in the bottom, we have timestamping, which basically allows parallel forks because there is no hash rate scarcity. The times you can timestamp many blockchains at the same time. So there is nothing to protect you from parallel chains. And then we have classical merge mining, where there is a specific space on the Bitcoin block, which is the Coinbase, where you will store a Merkle tree containing the different hashes of different blockchains that are being merge mined. And there is a one-to-one correspondence between a secondary chain block hash and this Bitcoin block. And then we have at the top of this hierarchy the fork-aware merge mining. The main difference is that in classical merge mining, 51% of the merge miners can attack you, while in the fork-aware merge mining, you need 51% of the total hash rate. In this case, it would be the Bitcoin hash rate in order to attack you, to attack the persistent property of the blockchain, right? So then we have several choices, and in the fork-aware merge mining, we can let each node take the decisions if it's being attacked or not, with certain information that we can add to blocks, or we can create an external system run by many external parties that can broadcast information to the whole network and inform in case of attack. Well, in this presentation, we are focusing on the local detection because we think that it will be easier. And even if it has a little bit more of false positives, I think it would be easier to implement quickly on the Ethereum Classic blockchain. So first of all, why we are not proposing merge mining Ethereum Classic with Bitcoin? So there is a couple of difficulties to bootstrap merge mining of Ethereum Classic with Bitcoin. One is an unclear strategic alignment between the two blockchains. Even if some people will be willing to, I'm sure there are certain miners that we won't want to. Then there are high operational risk on adding a new node to a mining pool system, because if something happens with the pool, then they will lose the Bitcoin rewards, which is their main source of revenue. So it's a very, very slow process. RSK has gone through it, and it's not something you can get overnight. And third, there are some block rating compatibilities. Bitcoin miners are not able to create blocks with new templates as fast as the Ethereum Classic blockchain needs, which is I think it's 13 seconds per block on average. Probably Bitcoin miners can only create one block every 30 seconds or every minute or so. And also, the Ethereum Classic community doesn't want to switch to SHA 2056. It has already decided to switch to SHA 3. It's interesting that RSK can provide Ethereum Classic with the system to merge mine with Bitcoin with 50% of hash rate. This is because RSK has a subsystem called Universal Merge Mining, which allows you to use RSK to buy Coinbase space for secondary blockchains. But again, I think that going through RSK for the main consensus of Ethereum Classic will not be accepted by the Ethereum Classic community, because it would be seen as, kind of strong dependency on RSK. And finally, the last reason, while you cannot do merge mining, or it's very hard to do merge mining with Ethereum Classic and Bitcoin, is that if you combine two proof of work functions, let's say we want to combine ETH hash or SHA-3 and SHA 2056, then you have a lot of problems with reorganization instabilities, because the thermodynamic weight of a Bitcoin block would be about 100, or I think it's more than 1,000 times more than an initial SHA-3 block. So essentially, the whole cumulative difficulty will come from Bitcoin blocks. So the other blocks will just not worth anything. They would just be reorg all the time when new Bitcoin blocks come. So it's not stable. So that's why we came up with this idea of visibility proofs. And I must tell you, this was very short. On very short notice, we designed this system especially for Ethereum Classic. So the idea is to reuse the merge mining infrastructure of Bitcoin and all the Bitcoin security, but as an optional second layer of defense. Okay, we are not altering the main consensus of Ethereum Classic. There's only one main difference with merge mining, is that we do not change the cumulative difficulty. Okay, so the rule that governs which change is the best chain is still the same. And these visibility proofs provide information to Ethereum Classic nodes to detect potential hidden attacks, or in case of an external monitoring system, it can even distinguish between an honest fork or many different honest forks going in parallel and a dishonest fork having a majority of the hash rate. And nodes can react to this information, automatically preserving the persistent property, as I said before, by going into a safe mode. And okay, the parameters of this system are not fully specified. We can tweak the numbers, but essentially the design is fixed here in this presentation. So I hope you can see this diagram clearly, but this is the flow where how new visibility proofs are built. And you will see that there are 3 blockchains interacting, but you can see RSK only as a mean to access Bitcoin miners. I mean, if you in the future could access directly Bitcoin miners in some other way, then you won't need RSK anymore. RSK here is just providing you the service to access 50% of the Bitcoin miners right away. So it all starts with a checkpoint. Okay, this is one every, let's say, 64 Ethereum Classic blocks, which is one of 64 is called a checkpoint. And once this checkpoint is confirmed, sufficiently confirmed, then there's a new actor we call a visibility proof miner, which can be a separate actor of the system, or it can also be a SHA-3 miner or an ETH miner doing both roles. But essentially, this visibility proof miner goes to the RSK blockchain and buys a slot of time to merge mine Bitcoin. And so he informs the RSK. This is done by a decentralized contract, obviously open source. Decentralized contract running on the RSK blockchain. So anyone can go and buy merge mining time. So once this happens, there will be a time, we think about 1 hour slots where the checkpoint hash will be merge mined with Bitcoin. And approximately 1 every 20, 1 every 40 RSK blocks is a Bitcoin block. So when that happens, we get what we call a hit, which is basically that we have managed to merge mine Bitcoin with Ethereum Classic blockchain. Okay, and when this happens, the visibility proof miner will extract the merge mining data, which is a proof that this Bitcoin block is related to the checkpoint, and we'll include that in Ethereum Classic block, and that increases this checkpoint weight or score in visibility. So we have a new type of new variable, which is the visibility score of a blockchain, and this value is computed over a period of time, a sliding window of time, and by including this visibility proof, we increase the score of this checkpoint. And what happens is that if there is another Bitcoin block that confirms the previous block, even if it doesn't have the merge mining tag, even if it was not mined by RSK, then this block still has merge mining, non-membership proof, I would say, non-merge mining proof. And it also serves as additional confirmation for the checkpoint, okay? So essentially, this is the way that the checkpoint is getting more and more visibility or visibility score. So what are the acceptance rules for visibility proofs? First, we request that the Bitcoin header has a timestamp that is very close to the checkpoint timestamp. Then we require that visibility proofs are included in the Ethereum Classic, not very far away from the checkpoint. And this is important. This is very similar to uncles in the Ethereum Classic blockchain. And we also require that visibility proofs are not repeated, just can only be used once. And a visibility proof will contribute to this score that is measured over a sliding window of time in the exact amount of its difficulty. So you have more difficulty, then you get more score in this visibility score. It's better if we add an additional consensus rule. This is something that it has a lot of it's very useful for security. That is, the best chain must end with the current time to be valid. You cannot create a best chain, even if it has higher cumulative work, if it just ends in the past. You won't accept that. And this does not bring any other problem to Nakamoto consensus. So what do we need to create this alert system? Well, we need two things. First, we need, as I talked before, a safe mode in case that the visibility score decreases. For instance, if we have a local for detection, then we can set a threshold like, let's say, 70%, where if the visibility score goes below this threshold in a period of time, then you enter this safe mode. And this safe mode, it's the node keeps running, keeps adding blocks. The only difference is that it won't confirm transactions in its RPC protocol. Okay, so if you connect to your full node, you won't get any transaction confirmed while in safe mode. And safe mode is self-healing. So when the attack ends, the node automatically goes back to normal. And well, there is another condition that you need to enter safe mode is that if the standard deviation of the block timestamps differs too much from the mean, and then you should enter also the safe mode. And if you have a separate alert broadcast system, then you can even distinguish from several forks to a single malicious fork because of additional information that is stored in the visibility proof tag. And you also need some form of penalization when visibility proofs are missing. Okay, so basically, if the density of the visibility proofs goes below a certain threshold, then you have to penalize that branch. You can just invalidate it. You can request more blocks, as Pilguard does, but essentially you just penalize it. So we will look at different examples of attacks, and we will show how visibility proofs react to those attacks. So here we have a honest Ethereum Classic chain. We have the violet blocks are blocks with visibility proofs. The red block has a payment to a victim. The victim is probably an exchange. And in 100 blocks later, let's say, there is a payment confirmation by the exchange, and then the attacker will, probably exchange Ethereum Classic coins for Bitcoins or Monero or some other coin. So the first attack is one that does not have visibility proofs. Okay, so it goes undetected, it's hidden, but when the attacker makes the chain visible because it has a higher cumulative difficulty, then this chain is rejected because it doesn't have the required threshold of visibility proofs. So essentially, this attack does not work. This attack is much more interesting. This is an attack where the attacker mines Ethereum Classic blocks in stealth mode. So it's not showing the Ethereum Classic blocks to the network, but it's still trying to use the visibility proofs, this system, to get visibility. So what happens is that visibility proofs will get split between the honest chain and the attacker's chain, And this is public. You can anyone can check this in the Bitcoin blockchain. And since visibility proofs are being included in blocks, and there is an incentive to include visibility proofs in blocks, then every node is aware that an attack is ongoing. And if an attack is ongoing, then it switches to safe mode. And in safe mode, it won't confirm the first payment confirmation, and it will only confirm the first payment when the safe mode is over, which may happen 100 blocks later. So the only I would say damage to the victim is that it has only to wait more time, but it never confirms the first payment. Then we have some other types of attack we are very easily deterred. Like what happens if the attacker waits for the payment confirmation and then start mining blocks very, very fast. He has a lot of ETH hash rate. Then again, he cannot do this because he has no visibility proofs, and visibility proofs cannot be easily backdated. We'll see more about that. And if he tries to backdate in the attack number 4, the ETC blocks, then he earns. I mean, there's nothing better. He cannot change anything by doing that. The last attack we'll be presenting is one that is combined with an isolation attack, where the attacker tries to pack a lot of ETC blocks with very, very few visibility proofs, like compressing the ETC block to get a higher amount of cumulative difficulty in a short time. And well, this will not work because of this rule that we added. I told you before that if the standard deviation of the block times of the Ethereum Classic blocks goes over a certain threshold, then the node also enters safe mode. Okay, so this attack also will not work. Okay, so this is the most the attack that is harder to defend, and this is an attack where the attacker does some visibility proofs, like 30% of the visibility proofs he does in real time, like trying to get below the threshold that nodes used, and then he tries to like let's say 24 hours later, when the payment in the exchange has been confirmed, he tries to backdate visibility proofs to fill the missing the missing visibility proofs during the first time. Well, this has two problems. First, these visibility proofs blocks, which are Bitcoin blocks, he has to backdate, so they cannot be valid Bitcoin blocks. And since they cost electricity because they are not subsidized by Bitcoin. So for instance, in this case, he has to fake, the attacker has to fake 57 Bitcoin blocks, and that it has a cost of about $3 million in electricity. But still, he cannot do this because he would need, just to extend this blockchain and make it a best chain, he would need to extend it to the current time. And for the attacker to do that, he will need to add visibility proofs to the remaining part, which is what it's after the payment confirmation. And to do that, the attacker would need 110% of the Bitcoin hash rate. So he needs more than all Bitcoin miners trying to attack Ethereum Classic. So we consider this kind of impossible. So okay, so I've talked about all the particularities of the proposal to Ethereum Classic. Now, Martin will explain more about what is this universal merge mining system that exists in RSK. Thank you very much, Martin.
Thank you, Sergio. So, well, up to now you've seen the details of how this would work for Ethereum Classic, but now you may be also wondering, okay, so how do we get the visibility proof, which is something very important for this system to work. So here is the thing. So RSK can now provide access to around 50% of the Bitcoin hash rate through merge mining, as Sergio already told you. And we believe that since the current situation of the Ethereum Classic network, this will be the fastest way to have visibility proofs. to actually reach a way to put the information you need into a Bitcoin block. And why is this? Why it's not? Why you just not do merge mining with Bitcoin and do not use RSK? Well, because it is not easy to onboard the Bitcoin miners. And there are many reasons for that. One is that the changes that you need to apply to the mining pool software are sensible, and some miners would say, well, we're gonna keep this, we're gonna take this very slow, and it takes time. The other is that you need to provide the right incentives, so the miners, the mining pools join, and there are many other reasons. So this is basically why we are now proposing that RSK is one of the best options. And actually, I don't know if the best, but the fastest option in order to get that information relayed to the Bitcoin network. And what I'm gonna speak about right now, it's basically in a nutshell. I'm gonna explain what's the system and what's on RSK side to make this possible. So as you know, as we've been talking in this presentation, so RSK allows the transactions and contracts to communicate with miners. So, and this communication with miners allows also to include data in through the process of merge mining in Bitcoin blocks. This process is what we call universal merge mining, which is still being developed, still in beta, but we've been working a lot on that over the past few months, and we have a clear road of how that, of the things that we still need to do in order to fully implement it. And one of the proposals for this universal merge mining thing to work, I'm gonna go through the next bullets, which are basically an outline of some parameters that this system needs to work, and most of them still need to be determined and probably will be open for the Ethereum Classic community to discuss, of course. So one of them is, so what's going to happen with the subsidy? Well, what we propose is that the subsidy will be 90-10. So 90% will go to the SHA-3 miners and 10% will be to the visibility-proof miners. So the information that you will relay through the RSK network to the Bitcoin network, and then those miners will be the RSK miners, which are also Bitcoin miners. Then these visibility groups will be included, and the slots that will be used to include that information into Bitcoin will be obtained by an auction system. And I'm gonna talk a little bit more in the next slide also. But our proposal is that it's gonna be one auction per day, managed by an open source RSK smart contract. And so that means that there's gonna be 24 1-hour slot auctions on that auction every day. Then this is also important that this visibility proof auction system will provide one Bitcoin block hit money back guarantee. So what does this mean? Well, basically this means that if you let's think about the following situation. So you got a slot to include that information into Bitcoin, and then in the next hour, so you have a chance of 6 blocks in Bitcoin where that information can be included. But then if that information is not included in any of those blocks, then the money you paid for that block goes back to you. So that's how it works. But given the amount of hashing power that now RSK provides, that's unlikely, I would say. So since this is an auction system, we need to provide an auction method for doing it. So Bitcoin auction is what we thought would be the best. So basically, it's a blind auction where the second bidder is the one that wins. So that's to explain it very fast. And then, this is just a small detail. I mean, Ethereum Classic checkpoint hashes can be submitted in advance for a slot. That's just more of an implementation detail than any other thing. So basically, the 3 bullets that says to be determined are the main important things of this slide. And now, and just to wrap up a little bit of how this works on our side, and how this, thanks Sergio, and how this joins with what Sergio already said about getting hashes and including it. This is more like a high-level view of the whole process for a visibility-proof miner. So the thing is going to start with the visibility-proof miner that you see over there on the left top side. That's going to buy these slots on the auction for the next 24 hours, as we said in the previous slide. So then the visibility proof miner is going to buy the slots to this smart contract that I also mentioned before, and it's going to have the right to include the information in the next slots. So whenever he needs to do that, what he does next is that he retrieves a new candidate block from the Ethereum Classic network. Then he generates a hash and publishes it, that a hash that represents that block or a range of blocks or whatever information you want to include in this slot he already bought, right? So he generates the hash, publishes it to the smart contract. And then the RSK network, it's going to start pulling the smart contract in order to see if the miner already provided the hash to be included in Bitcoin through merge mining. So suppose that the hash has been generated by the visibility proof miner, has been submitted to the smart contract, and then the RSK network, when it's going to mine the next block, just asks the smart contract and says, hey, do you have the hash? Yeah, I do. So the RSK network will then include this hash in the next to be mined block, right? This to be mined block will sooner or later be included in the Bitcoin network, as it says there on the arrow that says merge mining proof of work between the RSK and the Bitcoin network clouds. And then this is gonna be mined, as I said, sooner or later. And once it's mined, then the visibility proof miner can actually be listening to an RSK network node and see if the block has been successfully mined and included in RSK network and also in Bitcoin. So whenever this block gets included, then the miner gets aware of that, and when he's aware of that, he says, okay, well, then this is it. I just bought a slot, published the hash that got mined. It's now in Bitcoin. It's now in RSK. So what I'm going to do is I'm going to publish it to the Ethereum Classic network, and as a miner, I'm going to earn the rewards for that block, and the network is going to be more secure thanks to the work I've been doing. So this is just a general overview of how the whole universal merge mining flow would work for a visibility proof miner, and then you might imagine that inside those arrows there is the details that Sergio has introduced at the beginning of this talk. So that's pretty much it regarding universal merge mining on RSK side. So I think that now we are open to questions.
Okay, so there is one question. Does safe mode prevent only the attacker to make a transaction, or is the entire ETC network unable to transact in safe mode? Okay. So every node has its can make the decision to enter safe mode. So if you are not an economic node, you could disable safe mode in your own node. If you are an economic node and you are in that period you are accepting transactions of high value from the network, you will surely enter safe mode. So what I expect is that if there is an attack ongoing, then all economic nodes will enter safe mode. It will be all at once. I don't know. Maybe I don't know which nodes will not be willing to enter safe mode, but it's a local choice. Okay, so we don't have more questions. Tim or Brian, do you want to? Do you have questions yourself, or do you want to say something?
We've got a couple more questions at the bottom there.
Oh, great. Oh, yep. Great. Yes. Okay, what is the process you expect to occur after all nodes enter safe mode? New release with hierarchical checkpoint? No. The safe mode is self-healing. So because the node keeps extending the blockchain, internally does not stop working. It just stops confirming transactions to the user. So the node will receive information about what's happening on the visibility proof side. So when visibility proofs comes to normal, when one of the competing forks gets all the visibility proof again, then the node can get out of the safe mode and keep working as normal. And there are some parameters there that you have to configure, like how many blocks are you willing to wait after you were under attack to make sure that the attacker is not willing to continue the attack. And you can set that parameter to, let's say, 100 blocks or 1,000 blocks. It's really not so important. I would be very conservative because the existence of this system is a deterrent for an attack. So an attack should not happen if the system exists, even if it's never used. A new question: would ETC miners need to run Bitcoin and RSK nodes to verify visibility proofs? No. The interesting thing about visibility proofs is they are succinct and they are independent. You can validate visibility proofs without having any connection to a Bitcoin node. Because the visibility proof miners are the ones that are aware of the Bitcoin blockchain through RSK. They not even need to connect to Bitcoin. They just need to connect to RSK because all the information about visibility proofs is also in RSK. So no, there's no need to connect to Bitcoin. If you want to be a visibility proof miner, then you might want to, but it's not needed for a normal node. Okay, we have more questions. Team, if we run out of time, just tell me and I stop, right?
No, we're good for now. We're good for now.
Okay. Are RSK fees so predictable that they would be reimbursable by only such a simple change to the fee structure for an ECIP block? Okay, so I'm trying to get the idea of this question. So fees on RSK are very predictable. We have what we call a minimum fee that is published on every block. So wallets are, this is very similar to the ECIP that in a sense that the Ethereum Classic, the 1,559, I think. So we already have a minimum fee that is published on every block. So wallets tend to use that value as a reference. So there is no so much escalating fees on RSK. So yeah, they are more predictable. And also we have free space and gas in blocks. We are not in a point where we have so much congestion. But at the same time, if that would be a problem, we could just use the RSK network to communicate off-chain directly with miners, because we can propose this to the RSK community, and if it is something that they are willing to accept, then we could create a special, message to communicate directly with Bitcoin miners. Okay. Are full nodes fall into safe mode, or does every node? Can like nodes still transact, but it will be unsafe? Okay, so if any node detects that there is some form of attack ongoing, the safest thing to do is not to transact. If your transactions are very low in value, then you might expect that your transactions are included in both chains, in the attacker's chains and in the honest chain, right? Because most of the transactions, the simple payments can be just taken from one blockchain to another. So yeah, you could eventually transact even under attack. I think that it's not recommended, but you would be able to transact if the sender and the receiver agree to transact under under that situation. You mentioned a checkpoint in every 64 blocks. Any particular reason for that number? Oh, yes. That is because we need to get enough time for Bitcoin blockchain to produce a Bitcoin block for that checkpoint. I have some computations that why that number is a good number, but I don't have it with me, so I can send or publish this information why 64. But we could tweak a little bit this number, but it has to do with getting Bitcoin miners to have enough time to create a block. Considering that Bitcoin blocks also, they have some variance, some variability in block times, right? So what is the rationale behind having a blind auction for the process which is critical to securing another network? What happens if honest ETC miners get continuously outbid out of the UMM auction on RSK? They don't know how high the bid will win. Okay, so because Ethereum Classic will separate some amount of subsidy for visibility miners, and it's up to them to decide, then there is a clear limit on the maximum amount of value that will be required to acquire a merge mine block. So nobody would be willing to pay more than the subsidy. Okay, so I think that's if someone wants to control or pay more, then that would be obviously some kind of liveness attack to the network, and that's also why it has to have some value. And on the other side, we decided to do an auction because fixing any price will be even more problematic. Fixing any value, we would need an oracle to fix a value, let's say, denominated in ETC or in dollars. I don't know, but it would be far more complicated than making an auction. Okay. Do you have simulation on the operational cost of this solution? Visibility proof miner ETC reward should be bigger than the cost, right? Yeah, totally. Yeah, to incentivize visibility proof miners, the reward should be higher than the cost. And I think that the risk is fairly low for running a visibility proof miner, but since obviously for any complex system there is some risk, then there will be a difference between the reward and the cost, right? And simulations, no, we have not made simulations. I think that the system is pretty simple to understand, but yeah, simulation would be a good thing to do. Thanks, Julian.
Okay, I think that's probably about it now. Thank you, everybody, for attending, and particularly thanks to Sergio and Martin for your presentation today. I hope you've all found that useful and enlightening. Obviously, this is part of the process. I think we're hoping, Brian, to have another developer session a little bit later this week, so follow IOHK and all the usual ETC channels to find out more when we've got a date and a time for that. But look, hope this has been useful. Thanks again, guys, for presenting, and thanks to everybody for coming.
Thank you for bringing us here, and I hope we can collaborate in the future. If the Ethereum community wants to do some kind of mixed thing between the different proposals, then we are happy to collaborate and make this happen. Thanks. Thank you all for present here.
Great. Thanks, everybody.
Thanks, guys.
Bye-bye.
Thanks, everyone.
Bye-bye.
Bye.
Thank you all.